So today we're going on to section 9.3. And I did that this morning, except I was like halfway through the lesson before anybody said anything. Um, so 9.3 on relative rates of growth. So I saw this, and I don't even remember if this is in your textbook, if it's in another textbook, but I thought it was terrific. So in science fiction movies, or disaster movies all the time, they'll tell you that, right, this is growing and it's growing exponentially. And I always laugh because I'm like, no, it's not. Nothing grows exponentially for very long naturally. And pretty much, except for, money in an account, nothing grows exponentially even unnaturally. Right? Very few things do that for very long, which is why when we did the logistic curve, I was like, this is pretty cool because it starts off exponential, but then it switches to growth to a limit. So, how fast does an exponential function grow? So, imagine, if you will, that up here on the board, I have the x-axis marked in centimeters and the y-axis likewise marked in centimeters, right? So when x is 1, e to the x would be e to the 1, which is a little less than 3. Okay, so 1 centimeter over, a little less than 3 centimeters up. Once we get to 6 centimeters over, now 6 centimeters over, 6 centimeters, that's this far, right? Not even 3 inches. It's 403 centimeters up. So it's over 4 of these up when we get to here, right? This is how fast this thing is growing. It's practically vertical already. When we get to 10, it's 220 meters up. So when we get to here, right, about, I don't know, 3.5 inches or so, we're 220 meters up. We're like, I don't know, over 600 feet. We're over 2 football fields up when we get to 10. And you're like, okay, this is really growing fast. Now, this is part of why things can't grow exponentially for very long. You just can't sustain it. And then we get silly. If we're at 24 centimeters over, which is about here, less than a foot, we're e to the 24th, we're about halfway to the moon. And then at 43, so we're not even half a meter yet, so we're less than 2 feet, we're 5 light years up, if you wanted to graph it accurately. Okay, so exponential functions grow incredibly quickly. But what we want is we want to be able to go, okay, how can I compare how fast this function grows to how fast this function grows, right? So like x squared, it grows pretty quickly, right? It's not close to how fast exponential functions grow. But we need a better way than to just say, oh yeah, I feel like it doesn't. And we could make a similar list for x squared and it'd be like, okay, when we're 43 centimeters over, we'd be 43 squared centimeters up. I have no idea what 43 squared centimeters would be. 43 squared is 1,849 centimeters. So it's 18 meters up compared to e to the x, which is about 5 light years up. I mean, it's not close. But we need a better way rather than just comparing a few values. So that's what we're going to be looking at today. So let f and g be positive for x sufficiently large. So what that means is that we don't care what happens at the beginning, right? If until x gets to 20, neither of them is positive, we don't care, right? And then this is going to continue to grow, and f and g are both going to be positive. So we say that f grows faster than g, or g grows slower than f, either way you want to say that, as x goes to infinity, if the limit is f of x over g of x is infinity, or if the limit of x goes to infinity of g of x over f of x is 0. Okay, so what we're saying is that in terms of relative growth, even if both of them go to infinity, that if we take the ratio and it's infinite, well, this is growing a lot faster than g of x is, right? Not just, somewhat faster, but like I think about it as a different order of magnitude. It's a whole different kind of growth. Likewise, we can say that they grow at the same rate if this limit as x goes to infinity of f of x over g of x is equal to L, provided L is not equal to 0 and it's any constant. So let's say that I had something like 2x squared in the numerator and x squared in the denominator. 2x squared is always going to be bigger than x squared. But as a relative growth rate, they kind of grow the same way, right? They're the same type of growth. And if you took the limit of that, it would be 2, which is a constant that's not equal to 0. So we say they grow at the same rate. Even though one of them is always going to be bigger than the other, they grow at the same rate. Okay? All right. So, and I did one here where it's linear. Y equals 2x doesn't grow faster than y equals x does, even though y equals 2x is always greater than y is equal to x for positive values of x. Okay? So, let's show that e to the x grows faster than x cubed as x goes to infinity. So we're going to take the limit as x goes to infinity of, if I suspect one of them is faster than the other, I always put that one on top. I'm just more comfortable with it. So there'll be e to the x over x cubed. And this is why we did yesterday's lesson. The limit as x goes to infinity of e to the x is infinite, and the limit as x goes to infinity of x cubed is likewise infinite. So I can apply L'Hopital's rule. That'll be the limit as x goes to infinity of e to the x over 3x squared. So I look at both of those limits. The limit as x goes to infinity, e to the x I've already said was 0. And the limit as x goes to infinity of 3x squared is likewise infinite. So we can apply L'Hopital's rule again. So that'll be the limit as x goes to infinity of e to the x over 6x. Both of those go to infinity. I'm spending more time, justifying that I can use L'Hopital's rule than actually using L'Hopital's rule. So this will be the limit as x goes to infinity of e to the x over 6, which is clearly infinite. Therefore, e to the x grows faster than x cubed as x goes to infinity. So, and again, I have lots of thoughts about this, but one of the things that I think about is this is not the difference between an Olympic class sprinter and me, right? Although, they're going to beat me badly because I only run when chased. We're kind of the same order of magnitude. This is the difference between an Olympic class runner and a bullet. Right? They're not in the same. You're like, they're not even in the same game. Okay. All right. So let's show that natural log of x grows faster than the square root of x as x goes to infinity. Now the interesting thing about that is, just real quickly, if we think about it, the square root of x kind of looks like this. We usually draw a natural log of x kind of like that. Most of the time we kind of have it leveling off, and they both of them kind of level off, but it turns out the natural log of x grows faster than x to the 1/2 does. So let's show that. So we're going to have the limit as x goes to infinity of the natural log of x over x to the 1/2. Both of those grow pretty slowly, actually, to infinity. So we'll have the limit as x goes to infinity of 1 over x, bless you, over 1/2 x to the negative 1/2. And you're like, now, if I was to try and evaluate, the numerator goes to 0 and the denominator goes to 0, but I could be here all day taking derivatives over and over again, and it's only going to get worse. But after using L'Hopital's rule, we can still use some of those algebraic tricks. So I'm going to multiply top and bottom by x so that I can clear the complex fraction. So this will be the limit as x goes to infinity of 1 over, this is going to be 1/2 x to the 1/2. Which is 0. And you're like, oh, wait a minute. I thought it said natural log of x grows faster. This is one where I put it in wrong, and I just have never changed it. Turns out that since that's 0, that means that natural log of x grows slower than the square root of x. And we normally think of the square root of x as kind of growing slowly, but natural log of x is even slower than that. You're like, well, why is that? Well, think about how fast e to the x grows, right? Natural log of x is the inverse. So that means the x's and the y's exchange places. So that means, if we go back to this, in order to get to a y value of 43, we would need to have an x value of about 5 light years. That's growing incredibly slowly. So if you graph natural log of x, when you get away from the origin, if you move further over to the right, it looks like a horizontal line. And you don't even have to get that far over before you're like, oh, that's a horizontal line. You're like, nope, that's natural log. It's just growing really, really, really slowly. Okay? All right. Now, let's show that these two grow at the same rate as x approaches infinity. So I'm going to take the limit as x goes to infinity of the square root of x to the 6th plus x squared over x to the 3rd. This is absolutely not the time to try and use L'Hopital's rule, because you can see how incredibly ugly the numerator is going to get really, really quickly. Right, when we take the derivative, we're going to have to use the chain rule, and then if we had to do it a second time, now you've got a product rule, and you've got to do the chain rule within the product rule, and you're like, I'm not sure I'm ever going to get anywhere. And to get this to something where it's not going to be infinite is going to take a while, right? So here's the neat little trick, and that is to do this. We're going to take the limit as x goes to infinity. I'm going to leave the numerator alone. X to the square root of x to the 6th plus x squared. Now, because we're only putting in positive values of x cubed is always going to be positive, right? So I can say that this is equal to the square root of x to the sixth in the denominator. Now you do have to be careful about that. Again, it's because x is going to infinity that we can do that. If x was going to negative infinity, we would have to take the opposite of this, right? Because x cubed, if x is a negative value. And then what we'll do is we'll go, okay, let's do the limit as x goes to infinity of the square root of x to the sixth plus x squared over x to the sixth. Which, let's just look at the part underneath the radical, the radicand, if I remember the correct word for it. I don't use those words very often. As x goes to infinity, what does x to the sixth plus x squared over x to the sixth go to? Yeah. The dominant term for both the numerator and the denominator is x to the sixth. When you get really big, the x squared doesn't really matter that much, does it? I mean, comparatively. So this is going to be the square root of 1, which is 1, which is a constant that's not equal to 0. Therefore, both grow at the same rate. As x goes to infinity. All right, and then the last idea is this idea of the transitivity of growing rates. So if f grows at the same rate as g as x goes to infinity, and g grows at the same rate as h as x goes to infinity, then f grows at the same rate as h as x goes to infinity. All right? So f and g, same rate. G and h, same rate. So f and h, same rate. So you're allowed to pass through that. So that can make some of these a lot simpler. So when I look at f of x is equal to the square root of x squared plus 5, for positive x values, this plus 5 means almost nothing, right? The square root of x squared for x is positive is just x. So I can compare that to x and show that those grow at the same rate. And then I can do the same thing here. Right? Oh, this is the square root of 2 square root of x minus 1. The minus 1 means almost nothing. And as x gets really big, this 2 doesn't really mean anything either. It doesn't have much effect. And if I square the square root of x, I get x. So if I can show both of these grow at the same rate that x does, then I can say they grow at the same rate as each other. Now, why would I want to do that? Well, if I put f over g, I'm not quite sure how I'm going to rewrite that so that I can do something clever like we did on the last one. Okay, so on the last one, we could have compared both of these. Well, don't worry about it. We could have compared them both to x to the third power, but x to the third power is already what we were comparing it to. I was thinking one of them, they were both more complicated. So, I'm going to let h of x be equal to x. So the limit as x goes to infinity of the square root of x squared plus 5 over x is equal to the limit as x goes to infinity of the square root of x squared plus 5 over the square root of x squared. Again, that only works if x is positive, which it is. X is going towards positive infinity. So that's the limit as x goes to infinity of the square root of x squared plus 5 over x squared That's pretty clearly 1, which isn't 0. Therefore, f of x and h of x grow at the same rate. And then we'll compare g of x to x. So we'll have the limit as x goes to infinity of 2 square root of x minus 1 quantity squared over x. What do you think we might be able to do on that one? There's actually 2 different ways you could do it. Thoughts?
Can you take the square root of the top and bottom?
No, because that changes it.
Oh, okay.
We can't change its fundamental value.
Okay.
It's not a bad idea, but no, that, if you want the ratio of 8 to 12, if you take the square root of the 8 and the 12, now you've messed up the ratio. We need to algebraically manipulate this in some way. All right. Well, here's what we can do. I'll show you one way. We could rewrite that as the limit as x goes to infinity of 2 square root of x minus 1 quantity squared over the square root of x squared. Right? Sort of using that same idea we used on the last one, just in the opposite direction. So it would be the limit as x goes to infinity of 2 square root of x minus 1 over the square root of x all squared. As x goes to infinity, this negative 1's not going to matter worth a hoot. If I divide 2 square root of x by the square root of x, I get 2 squared is 4. It doesn't matter that it's not 1. You're going to get 1 a lot, but there's nothing magic about 1. But I know that that's not equal to 0. So therefore, g of x and h of x grow at the same rate. So, since g of x and f of x both grow at the same rate, as h of x, g of x, and f of x both grow at the same rate. As x goes to infinity. By the way, the other thing I was thinking about that you could have done is you could have just gone ahead and squared. Right? And you would have gotten 4x minus 4 square root of x plus 1 all over x. And as x goes to infinity, this is the most powerful term in the numerator. It's going to go, and then the most powerful term in the denominator is x. 4x over x is 4. All done, and you don't have to be quite as clever. All right. Any questions about that? Okay. Well, that is all I've got for you today. I have no idea what time this class is over. Oh yeah, 9:45. Okay. We have plenty of time still left.
Hey, restroom.